Now, let us briefly talk about one-way slab. So, as you can see, when the ratio of longer to shorter side is more than 2, then the slab is going to bend predominantly in one-way direction. That means, my main reinforcement I have to put only in the direction of bending where I have more curvature, right. So, that is the definition for an one-way slab. Now, again one-way slab also can be post-tensioned and one-way continuous slab also can be post-tensioned, right, to lead to more economical design. Now, under the action of loads, one-way slab deflects in the shorter direction only in a cylindrical form. Therefore, main reinforcement is placed in the shorter direction. And in the longer direction, we provide the shrinkage reinforcement. For example, this is one case that what you see here. I have oriented some lateral frames in the red color. What you see here in this picture is actually is a floor joist one-way slab with girders on one side. So, that means what is the meaning? You see here I run the girders like this, right. Yeah, also I have some girders on the perimeter, okay, perimeter of the building just to stiffen it up, but all these other things are actually one-way slab. So, for example, this is a one-way slab, and as you can see, this is B and this is A. Definitely B by A is greater than 2, right. So, it is going to be a one-way slab like what you see here. This is a one-way slab. So, this is your support and this is your support, and you can see the distance over which it is spanning is quite high. So, it is going to bend like this, right. So, it is a one-way bending, right. So, predominantly it is going to bend between the supports, right. Now, these slabs also can be either post tension or pre-tension, but typically if these elements are made in factory, it is easy for us to do pre-tensioning, because I can make more number of products by going for a long line method of casting. So, such kind of elements are usually done using pre-tension, right. That can also be done, right. So, this is one-way slab. So, one-way slabs are also they are pre-stressed, either it could be post-tension or pre-tension, but if the slabs are made in factory, typically they are pre-tensioned, right. Now, let us look at the design of a one-way slab. So, one-way slabs are analyzed using design moments by considering a unit width of the slab, considering the dead and live load contributions, just like what we do regular flexural design, and pre-stressing force and eccentricity of the cable are required at the prominent sections to resist the dead and live load moments are found out. As you know, you do the analysis, bending moment diagram distribution you get it, and the cable profile should follow actually the bending moment diagram. So, that is because you are going to put reinforcement wherever tension is going to develop. That is the reason typically most of the places we draw the bending moment diagram on the tension side. So, to know where to put the steel. Pre-stressing steel is also, it is actually steel that helps in resisting the tension. So, we need to put where the bending moment are there. For example, this is a slab and it is going to bend in the shorter direction. So, the spacing of the cables or wires is fixed based on the availability of the type of tendon and the slab configuration. So, for example, this slab, if you take it, it is a one-way slab, it is a one-way continuous slab, it is a one-way continuous slab, right. Okay. So, the concentric tendons are generally preferred for transverse pre-stressing of the one-way slabs to prevent objectionable deflections in the transverse direction, right. So, what is the meaning? So, typically what we try to do, in one-way slabs, especially for a short, single span, okay, this is particularly for a single span. When you make it, what will happen, you tend to have, if you put it at an eccentricity, then your camber may go up, right. So, that has to be designed properly, right. So, that is the reason typically what we do is we do not change the cable profile, we just try to keep it at the same eccentricity, that is why they are called as concentric tendons, right. So, the cable profile does not change, okay. So that we can prevent objectionable deflections in the transverse direction. Right. The slabs designed again of course should also conform to the requirements of serviceability and the strength, right. And most of the time the amount of pre-stressing cable is designed for stress limits and to satisfy the deflection, and if you do not satisfy the strength, then what we can do is we can put some additional non pre-stressed regular your TMT rebars, right. Now, one more thing. So, when it comes to one-way slab, hollow core slabs are very commonly utilized in commercial buildings as well as in residential construction. They are actually precast, pre-tensioned floor elements, right, because they are made using this long line method of casting, and typically they have a longitudinal core that will be running along the span, primarily provided to reduce the self weight. As you know, again the slab weight is the major dead load contributor in a typical residential and office building. So, if I can remove the area, and these are typically flexure governed, okay, shear flexure governed. So, for flexure, you know, I section is the most efficient cross section. So, the hollow core also, if you idealize this, if you remove all the core, it can be converted into an equivalent I section, right. So, it is a very efficient cross section for flexure, and because I am putting pre-stressing, that also helps to increase the shear strength close to the support, and usually they are all simply supported like what you see here, right, and it is very efficient for longer spans. So, hollow cores, that is the reason they are one of the most used precast elements, and they occupy almost 50%, 57% of the market value if you look at the overall precast industry, right, because you see, if you look at various elements that are being made by the precasters, frame element they occupy about 22%, cladding elements they occupy about 21%, but 57% is actually precast hollow core units, right. So, this is coming from one of these references that here. Now, with this hollow core elements, now what we can do, I can make them lightweight, and I can also change the density, and you can also use them as a wall panel or as a facade element. I can also make it load bearing also, and I can also use it as a roof and slab element, right. So, multiple purposes can be made. In fact, the hollow core can be used as a slab element even in a steel construction or a wood construction, right. So, in that way it's going to give you very good fire resistance as well. So, in that way it is very commonly used precast element across the industry, and they are pre-tension and precast one-way slab element. Right. So, quickly, what are the advantages of pre-tension hollow core slab? Because they are very lightweight, they are very quick and easy to install, like the one that you see here, and these are all spanning like this in each direction, right. And then they reduce the self weight, as we have discussed, because we have removed the weight in the center of the hollow core by that's an example. So, for example, if you take 3.1 meter by 150 mm slab with a width of 600 millimeter, you get the weight as 670 kg. The same thing if I make it as a hollow core, now the weight becomes 406 kg. So, there is a reduction of almost 40% of the dead weight. So, again from residential construction point of view, reduction in dead weight will lead to very high savings in cost, right. So, the next one is it leads to big cost saving, and then it has excellent fire resistance, because you know the core will be filled with air, and air is not a good conductor of heat. So, it gives you very good fire resistance, and they are very highly efficient sections for flexure. So, they offer high load capacity and flexural rigidity, and then they have excellent thermal and acoustic insulation, because again air is a poor conductor, and then it can be used in seismic zone. So, now how do you use it in seismic zone is we can design the systems and create a topping slab of adequate thickness, so that a diaphragm action can be achieved. And I can also create some cores opening in this hollow core and then fill some concrete to create better integrity with the topping slab, right. So, and production flexibility, now I can put I can make any thicknesses for usually for even bridge applications. Hollow core elements are used for spans of up to 20 meters also. Now, with all the advent of high strength and ultra high performance concrete, now hollow core elements can be made for supporting even for a very long spans, right. So, these are all some of the advantages of pre-tension hollow core slab. Now, let us quickly go through one design example for a one-way slab system. It is very similar to a flexural beam example, but the idea is to show how a bridge deck slab up to 12 meter can be designed as a one-way slab, okay. And we are saying that we are going to use cables that will have a capacity of 650 kN. Now, I need to find out what is the thickness of the slab and what should be the amount of pre-stressing and what should be the layout of this cable. Only the requirement they have given is the cable available is each cable can give you a force of 650 kilonewton, right, from the manufacturer. So, the deck slab is required to support an uniformly distributed live load of 20 kilonewton per meter square. It is quite high because the live load is a bridge deck slab that we are talking about. So, requirements are high. And design, now we need to design the spacing of the cable and their position at the midspan section. So, let us assume pre-stress loss to be 20%, right. So, and these are the acceptable stress limits. So, you can see when you transfer, we need to make sure that for example, the compression cannot go more than 15 megapascal and tension cannot go more than 2.5 megapascal. So, let us look at now how do we design it. Now, first thing is we know the load, we know the span. So, we can live load requirements are given. So, I am going to take 1 meter width slab and then see what are the demand that what we are getting, right. And we know from PTA manual for a one-way slab, span to depth ratio for post tension slab can be taken from 45 to 50. Now, here we are taking 45. So, effective depth requirement works out to be 267, and then if I am assuming a, let us say, a cover of 25 mm with effective cover, then I am taking a round value of 300 millimeter. Okay. So, and definitely it will satisfy the requirement. So, you can see and of course, the cover requirement should be followed from fire resistance and durability requirement. Typically, minimum is nominal cover of 25 mm is assumed, and then because you are going to use a flat tendon, the tendon duct size will be usually, and they are also mostly in the Asian countries like in India, we do bonded system. Unbonded systems are used, but they are not that commonly used. Mostly it is a bonded system. Then we put cover as minimum cover is 25 millimeter. Then if I put again another 12 mm as the effective cover for the reinforcement. So, then you 300 mm works out to be okay. So, let us take a round number of 300 mm, let us check. Okay. So, now that I have assumed the thickness of the slab, so for 1 meter multiplied by thickness and multiplied by the unit weight, I get a load of 7.5 kilonewton per meter, and live load is given as 20. For 1 meter width, it is 20 kilonewton per meter, and so total load is 27.5 kilonewton. So, you can see for this PT slabs, because thickness is only 300 for 12 meter span, the live load, the dead load requirement is lesser. And now, these are simply supported. So, total load moment is WL square by 8. So, I get a moment of 495 kilonewton meter. Now, we have seen that this cable can take for one single cable from the manufacturer data. Okay. They say for each cable it could be one tendon with a 3 cable or 4 cable or 5 cable. So, let us say that 650 multiplied by 0.8 is 520 kilonewton. So, we say that each cable can give only 520 kilonewton. Now, what is the amount of total pre-stressing required? I need to find out. Now, I know the moment, and if I divide the moment by lever arm, we know how much from your force method, we know that. So, if you take like this is your, let us say, PT cable. So, this is your tension force, we see that this is your compression. So, the movement of compression to tension will give me the lever arm. So, you can see moment by Z will give me the effective pre-stressing force. So, because C is equal to T, which is equal to your effective pre-stressing force. So, we can find effective pre-stress by dividing the bending moment with the lever arm. So, now lever arm I am going to assume for a typical one-way slab 0.8 times D is a good number. So, again design is an iterative process. So, after that if you want to optimize slightly, you can change it also, right. So, 0.8 to 270, so I am assuming 216 millimeters. So, once I know the lever arm, I substitute that and I get my effective pre-stressing forces bending moment divided by the lever arm, that gives me a force of 2291.6 kilonewton for 1 meter width, right. So, the number and spacing is going to be, now one cable can give me 520 kilonewton. So, this much force I have to apply by at least providing 4.4 cables. So, we can say, let us say we are providing 5 cables. So, 1000 by 5 will give me 200 millimeter spacing, that is a good round number, right. So, now determining the cable eccentricity. you can see it's going to be h by 2 minus cover, which is going to be, I am assuming some 40 mm cover. So, 300 by 2 minus 40, which gives me 110 mm from the bottom fiber. Now, using now that we find the pre-stressing force, we know the eccentricity. Now, I can quickly check the stresses. At transfer, we are using P naught by A. Concentric component is P naught by A, which is negative 2.16 megapascal. Bending moment, pre-stressing bending moment is giving me 4.76 megapascal, right. Dead load is 1.5 megapascal. So, if you add all of them at the bottom fiber, you see here I get a net stress of 1.1 megapascal, which is less than 2.5 megapascal. So, that means whatever that amount of pre-stressing that I provided, it is satisfying the stress at the bottom. Okay. Sorry, this is at the top fiber, right. So, top fiber here it is going to produce compression. Right. So, this is going to be tension, right. Right. Pre-stressing moment is going to produce at the top, it is going to be tension. So, if you add all of them, so you get basically 1.1 megapascal. A transfer, you know that it is going to have a tension condition here, right. So, stress at the bottom fiber, again we do that, only the signs will change. We have done the analysis for stresses. So, all the magnitudes remain same. Now, this is in compression. Now, you can see here this is in compression again, pre-stressing moment will produce at the bottom fiber compression, and the dead load is going to produce tension. So, if you add all of them, I get again here also negative 5.42 megapascal, which is less than 15 allowable value. So, we are satisfying the stress level. In fact, we are quite comfortably we are satisfying the stress limits. If you still want to optimize the design, now with all these things I can reduce the number of cable to, instead of 5 cables, now I can go to 4 cables and then still do the checking for coming up with an optimized design. So, that also you can do. So, even if you put your 4 cables, you may still be able to satisfy the stress limits. So, you can see this is the cable profile that what we are having. This is the section view at the midspan, and you are putting 5 cables at a spacing of 200 millimeter, and this is for a thickness of 300, and you can see that the eccentricity is 110 millimeter. So, slab depth is 300 millimeter, and pre-stressing cable is 5 cables per meter spaced at 200 mm. So, when you put the cable spacing, try to keep a very round number, so that it is easy for us to implement it in the field. And now, tendons are placed at an eccentricity of 110 millimeters. So, a very simple example that we have looked at it. So, we can summarize what we have discussed in this module. We have explained the types of slabs, and we have also explained the analysis and design considerations for post-tension slabs. We learnt about distribution of tendons in slabs and their punching effect on the column, punching shear, we looked at it. We also discussed one design example on one-way slab for a bridge deck. So, in the next part, we will talk in terms of design considerations for PT two-way slabs in detail, and then go from there. So, thank you.